Determine if each infinite series converges or diverges. Looking at both infinite series, notice we have alternating series because the formula for the first series involves negative 1 to the power of n plus 1, and the second series involves negative 1 to the power of n. Because of this, we'll be applying the alternating series test. For a quick review, for the alternating series test, we first identify a sub n, which is a non-alternating part of the formula. The alternating series converges if the limit as n approaches infinity of a sub n equals 0 and the terms of the series are decreasing, meaning a sub n plus 1 is always less than or equal to a sub n. For the first series, we have the sum from n equals 1 to infinity of 3 times negative 1 to the power of n plus 1 divided by n to the power of 0.5. Notice a sub n, the non-alternating part of the formula, is 3 divided by n to the power of 0.5, which we can also express as 3 divided by the square root of n. And now we'll determine the limit as n approaches infinity of a sub n. As n approaches infinity, notice the denominator increases without bound, the numerator stays at 3, and therefore the fractions get smaller and smaller and approach 0, and therefore the limit is equal to 0. So the first condition has been met, and now we need to show that the terms of the series are decreasing, meaning a sub n plus 1 is less than or equal to a sub n. Using the formula for a sub n plus 1 equals 3 divided by the quantity n plus 1 to the power of 0.5, and we know a sub n is 3 divided by n to the power of 0.5. Recall when comparing fractions with the same numerator, the fraction with the larger denominator will always be less than the fraction with the smaller denominator. From here, the quantity n plus 1 to the power of 0.5 is always going to be larger than n to the power of 0.5, and therefore 3 divided by the quantity n plus 1 to the power of 0.5 will always be less than or equal to 3 divided by n to the power of 0.5, meaning the terms of the series are also decreasing. This indicates the given alternating series converges by the alternating series test. Looking at the second example, notice a sub n is 3 times 2 raised to the power of negative 0.6 divided by n. Writing this using a positive exponent, we have a sub n equals 3 divided by 2 to the power of positive 0.6 divided by n. And now we'll consider the limit as n approaches infinity. Notice 0.6 divided by n gets smaller and smaller and approaches 0 as n approaches infinity, and therefore the limit is equal to 3 divided by 2 to the power of 0, which is 3 halves, which doesn't equal 0. We can go ahead and stop here. This indicates the non-alternating series diverges by the nth term divergence test, and therefore, so will the alternating series. Or if we want to be more formal, we can apply the nth term divergence test using the original formula, and we know if the limit as n approaches infinity of the non-alternating formula approaches 3 halves, then the limit as n approaches infinity of the alternating formula will oscillate between positive 3 halves and negative 3 halves, which indicates the limit doesn't exist, and once again indicating the original alternating series diverges by the nth term divergence test. Before we go, remember, when applying the nth term divergence test, if the limit as n approaches infinity of a sub n doesn't equal 0 or doesn't exist, this does indicate the infinite series diverges. I hope you found this helpful.